Hi, everybody. Oliver White here, your friendly neighborhood newsletter slash webinar guy. With me today is Iulian Dragos, the team lead for Spark at Typesafe. Say hi, Iulian.
Hello, everyone.
So while I introduce Iulian, I'm going to pop up a quick poll asking about your dealings with Spark. Now, Iulian is almost at Scala graybeard, even though he's probably not old enough yet. He's been working on Scala since 2004 when he joined Martin Odersky's research lab at EPFL in Lausanne, Switzerland. This is where Iulian wrote the JVM backend, the bytecode optimizer, and worked on various other parts of the compiler for Scala. Now he's mainly focused on making Spark a fully fledged first-class citizen of reactive systems. So that's why he's a particularly good person to show you today various deployment modes for Spark, like standalone, Spark on Mesos, and Spark with DCOS and in the cloud. An overview of Mesos and how it relates to Mesosphere DCOS, the commercial side of the tool. A deeper look at how Spark runs on Mesos, and how to manage coarse-grained versus fine-grained scheduling modes on Mesos as well. Also a bit to know what about client versus cluster deployment, and we'll actually finish up by showing you a demo running Spark on Mesos. Now, while we're on the subject, Typesafe has been actively contributing to the Apache Spark project since 2014, and we're actually a certified development support partner of Databricks, the company started by the creators of Spark. We've also forged a partnership with Mesosphere, in which Typesafe is the official commercial support provider of Spark on Mesos, along with Mesosphere DCOS. And recently, as if we didn't have enough, partnerships with IBM with their Spark Center and data stacks to bring Cassandra into the mix have also recently been announced. And it's our customers that value strategic partnerships like these and our expertise that makes today's webinar possible. So whether you're starting off with Spark or running it in production, ask us about full lifecycle support for core, SQL, and Spark streaming, what kind of deployment models, including Mesos, DCOS, EC2, hybrid cloud, standalone, bare metal, you name it. If you want the full Typesafe experience, we have an optional 10-day Getting Started with Spark services package, as well as training courses and other great stuff with experts. And of course, all of this comes with unlimited expert support for your team. All right, enough from me. Let's turn it over to Iulian.
Thanks, Oliver, and yeah, sorry for this mishap. I guess that's a good start for a presentation about software, because it can always go wrong. And one of the good things about Apache Spark and Mesos is precisely that they allow you to build fault-tolerant systems. So without further ado, let's start today's webinar. And here's a very brief overview. I'm going to start with a few slides and a few words about Apache Spark, but that's not really the focus of this webinar. So I will not talk about Spark's APIs or what it enables you to do so much, as I'm going to talk about how you deploy Spark in production. And we're going to look a bit under the hood of Spark's cluster management, and then we're going to look at different ways to deploy Spark, focusing particularly on Apache Mesos. And everything we're going to talk about today applies to DCOS. And when we get there, I will explain what is the difference between Apache Mesos and DCOS. I'm going to talk briefly also about why we, Typesafe, believe that Apache Mesos is the winning solution in big data as a deployment platform, and why we chose particularly this configuration to support as part of our support. I'm going to show a couple of diagrams then explaining how Spark and Mesos communicate and how deployment actually happens under the hood. And then we're going to have a demo where I'm going to run a couple of very simple Apache Spark jobs, and I'm going to show you how they actually get deployed on Mesos. All right, so let's start with Apache Spark. I guess most of you by now have heard about Apache Spark as being the next generation big data solution. And Spark really took the big data world by like a storm. It became probably the most successful project in recent history, open source project, precisely because it is extremely fast. So compared to Apache Hadoop, the MapReduce compute engine, it's reportedly 100 times faster, and that's because it keeps data in memory, and it has a number of other optimizations that it can apply under the hood. It's also built with Scala and Akka, which is particularly interesting for Typesafe, being a technology that's built on top of our core competencies. So just a bit of history. Spark started almost 5 years ago at Berkeley, but it became an Apache project only in 2013 in the incubator, and then a year later, I think, it became a top-level Apache project, amassing over 400 contributors and moving at an impressive speed. So one thing that is important to keep in mind is that Spark does not replace the whole Hadoop ecosystem. It is just a compute engine, so it corresponds to the MapReduce compute engine that it replaces and does it very well. And also, as a consequence, it integrates and works well with the other elements of the big data ecosystem, such as HDFS or Hive, HBase. And actually, this is probably an interesting point when we get later to Mesos, because Spark does not run in isolation. Usually, Spark users and Spark deployments that we've seen at our customers have a number of other technologies like Kafka or Cassandra or HDFS deployed together. So I do have one slide about Spark API and what is so interesting about it. And Spark we can briefly describe as Scala distributed collections. So the power of functional programming that you have in Scala is actually augmented by distributing those collections on many nodes. So you can run Scala operations on hundreds or thousands of nodes. An interesting aspect of Spark is that it's not Scala only. It works, or it has APIs for Python and Java, and I think recently R is probably still experimental, but R, the statistics language, can also take advantage of Spark's execution engine. So you can run R expression or programs and work on big data. Another defining aspect of Spark, or a distinct feature of Spark compared to MapReduce, it's the interactive shell. You can type expressions on the command line and get an instant answer, or let's say a very quick answer without actually having to submit a job as a jar and go through the submission. But of course, you can do that as well. And this is what we're going to use today during the demo. I'm not going to build a whole application that I submit to the cluster, but I'm instead going to use the Spark shell, which is very convenient for experimentation and for demos like this one. But even in day-to-day life, sometimes what you have to do is small enough that it's not worth going through building a whole project. Streaming is another defining feature of Spark. So streaming has the same API as Spark Core, so the batch mode, making it very easy to adapt algorithms that work on batch data or analysis and run them as data arrives. So basically minimizing the time between when data arrives in the system or in an organization and getting results or getting value out of the data. So of course, around Spark, there's an ecosystem of itself, like Spark SQL, machine learning libraries, a graph processing library like GraphX, and so on. So let's now have a look at the way a Spark program executes. So in this diagram, on the left side, we have the driver program, and in there there's a Spark context, which is really the core of Spark. The driver program is the entry point in a Spark application. That's what starts the main, if you will. On the right-hand side, we have the cluster and the worker nodes. So the worker nodes are, they can be in the cloud or on-premise. They are simply machines on which Spark can launch executors. And executors are processes. They are launched by Spark cluster manager, and let me just turn that off. So in the middle, we have the cluster manager. And the cluster manager is, let's say, the master. It's what the driver program communicates with in order to acquire resources on the cluster, so these worker nodes, and then to launch the executor processes in there. And as the program, the Spark application executes, and RDDs, which are the distributed collection, get transformed and reduced and grouped by and so on. Tasks, which are sort of small transformations for one partition in the RDD, are sent or are shipped to these executors for execution. So those are the little tasks in there. Of course, to make Spark fast, there's a cache in there which keeps data in memory. So worker nodes can communicate in between them, not just with the master or with the driver, in order to read these cached data or shuffle files. So we'll come back to shuffle files when we talk about dynamic allocation a bit later on, but keep in mind that nodes have to talk between each other as well. So Spark abstracts over the exact cluster configuration. So the cluster manager can be something else in different situations. And the simplest deployment possible, it's called local. And this is very useful for experimentation. It means there is actually no cluster. Everything runs on the developer machine. It can be a laptop. So this is basically one machine that runs the driver, the cluster manager, and the worker nodes all in one. But of course, it's a bit more efficient. There won't be separate processes for all of this. If we move up in, let's say, the level of complexity and flexibility, there's a standalone mode, which is basically the Spark built-in cluster manager. So standalone is quite easy to set up, and there are scripts that come with the Apache distribution that just spawn a standalone cluster, be it on Amazon EC2 or even locally in your local network. But standalone does not have a lot of features. So if we move one level up, there are two, let's say, roughly equivalent cluster managers right now. One is called Yarn, yet another resource negotiator, which is the Hadoop cluster manager. So organizations that have already a Hadoop cluster running MapReduce or HDFS and so on, they can also run Spark on Yarn. Or there's Mesos, which is a general cluster manager, and this one is the solution that we prefer at Typesafe. And Mesos is a cluster manager that can run different applications, not just big data applications like Spark. So let's have a look at Apache Mesos. How should I put it? The tagline for Apache Mesos is program against your data center as a single pool of resources. So it's a general distributed kernel. So the analogy can be taken further to the OS. And Mesos provides efficient resource management by allowing sharing a pool of resources. And by resources here, we mean CPUs or memory or cores, if you will, volumes, even ports or the bandwidth, and so on. We'll see in a second how that happens. Mesos is proven technology. I think it has probably the same age as, or maybe it's even a bit older than Spark. And it's been deployed in production in very large deployments, like Apple. I think Siri is running on Mesos, and Twitter is using Apache Mesos, and probably a number of others as well. Now, when it comes to Spark, the bits and pieces inside Spark that make this deployment possible, they're maintained by Mesosphere, the company behind Mesos and Typesafe together. So we're partnering, as Oliver announced earlier, and we're making sure that this integration works as perfectly, so as good as it can be. So we're sort of betting here on Mesos being the winning long-term solution for reactive big data applications. And that's because you don't need separate clusters for running Hadoop Yarn or another one for Cassandra, and if you're running Kafka, yet another one. But they can all be managed together through the same, let's say, Apache Mesos, through the same platform. So when talking about Mesos frameworks, come along quite often, and this is simply terminology in Apache Mesos to refer to applications that run on Mesos. There's many frameworks already, so you can run on your Mesos cluster HDFS, the Hadoop distributed file system. You can run Cassandra, you can run Elasticsearch, and very interestingly, you can also run Yarn through a project called Myriad. And this is probably an interesting transition solution for people who still run MapReduce jobs, but they want to move to something more general like Apache Mesos. Now, Myriad is a project that is still quite young, so even though it's deployed in production, I would say it's still not as mature as Mesos or Spark itself, but it's very promising. Marathon is another framework which manages long-running services, and of course there's Spark. Now, how does Mesos deal with resources? So Mesos introduces a thing called two-level scheduling, and this is a pretty interesting idea. So the Mesos master has a number of slaves, and as frameworks start and stop, these slaves can be busy or they can be used up. But as frameworks exit, resources become available. So Mesos decides then, based on its allocation strategy, to offer those resources to one of the other frameworks that are still registered, that are still running. So this is the first level of scheduling. Whom does Mesos offer resources that are available on the cluster? Now, the second level of scheduling comes when a framework accepts one of these offers, which can be 8 CPUs and 4 gigabytes of RAM. So once, let's say, Spark accepts an offer, it is up to the framework itself to decide how to use these resources. So this would be the second level of scheduling. And here, Spark would deal with tasks, which are framework-specific units of execution, and others regarding ports or memory and so on. Okay, so let's have now a look at an example. In this diagram, we have at the bottom part a number of nodes. They are called Mesos slaves. And at the top part, we see on the left side the Mesos master and a couple of frameworks that are running there. So we have HDFS. It's depicted in green. So the HDFS framework is already using at least 2 nodes from what we see in the diagram: the name node and the data node. And on the right-hand side, we see there's the Spark framework, which would like to schedule a job. And let's now assume that the first slave, the first Mesos node, has some free resources. So in a first step, this node would just go to the master and say, I am S1 and I have 8 CPUs and 32 gigabytes of RAM available. In the second step, which is actually the first level of scheduling, the Mesos master decides that Spark should get these resources. Spark at this point decides that the best way to use them is by launching 2 tasks on the same slave, each one using 2 CPUs and 8 gigabytes of RAM, and whatever is left will be reused by the Mesos master. Of course, they don't get lost, and other frameworks get the chance to run it. In the next step, the Mesos master launches an executor, which is a process on the Mesos slave, and starts executing the task that Spark wants it to execute. All right, so I mentioned earlier that Spark abstracts over the cluster manager. So the cluster manager in Spark can be, in standalone mode, its own built-in manager. But for Yarn, it is really the Yarn master or resource negotiator, and for Mesos, it's really the Mesos master. So some of this terminology may be confusing because, interestingly, both Spark and Mesos originate from the same research lab in Berkeley, so they do use some of the same terms for slightly different things. So in Mesos and Spark, executors refer to slightly different things, but I think that if you're careful, this won't be too confusing. Okay, so let's move on now to how does Spark schedule, so the second level of scheduling. How does Spark schedule its own tasks with regards to the Mesos tasks? And the first mode is called a coarse grain mode, in which Spark acquires a number of resources as soon as it starts up. So the moment the Spark context gets created in your Spark application, it starts communicating to the Mesos master, and it acquires a number of slaves or executors. Let's call them executors. And for the duration of the whole job, for the whole application, the whole Spark application, these nodes will be reserved and they will be used by the Spark application. They cannot be used by other frameworks. This has advantages. In principle, your application will not have a lot of time to wait for starting up a new task, because the resources are already allocated and the Spark executor and Mesos executor are already launched when you start. So this is better for iterative sessions. Imagine that you're typing at the Spark shell. Every command or every expression that you type there is going to be fast because it reuses the executors from the previous one. The problem is that a Spark shell can be forgotten by somebody running, and the whole cluster now loses resources that are reserved and used by Spark, but not really used because no tasks are really running. Just a cursor is displayed and blinks, but nothing actually runs on the cluster for those things. So this is the coarse grain mode. There's dynamic allocation that was implemented or is launched in Spark 1.5, so I'm going to show that a bit later. That improves the situation. But let's look now at another strategy for scheduling, which is called the fine-grained mode. And in this situation, Spark does something very different. On startup, it registers as a framework to the master, and it starts getting resource offers as they become available on the cluster. But it doesn't launch anything yet. Instead, it waits until there's a Spark task, so a transformation that, or an action that requires to execute something on the cluster. And these kind of transformations are usually broken down into small tasks that are per partition, and this task can be hundreds of them in just one action or job. And for each one of those, Spark accepts an offer and launches a Spark executor for that task. So obviously, when there is nothing to execute, again, taking the example of the Spark shell, the cluster is completely free. So Spark will not add any executors or any tasks to run on Mesos. Instead, it just sits there as a registered framework, but does not accept any offers. So definitely, this leads to better resource utilization, but to a slower startup for tasks. It's obvious because it needs to launch a couple of processes, and it needs to set up the executor before it can actually service a task. So it's fine for batch and relatively static streaming, but for interactive jobs, this may add a delay between the moment where you want to execute something and the moment it can actually do that. So I mentioned earlier dynamic allocation, which is an attempt to bring something from both worlds. It's sort of a middle ground solution. And the idea is, well, what if we could have a number of executors that we reserve, as in coarse grain mode, that are always available, but if tasks start to queue up in the scheduler and they're starting to basically wait because all the executors are busy, let's add more executors from the Mesos cluster. So if new resource offers arrive, let's grab those and spawn new executors and run tasks on those. And conversely, when these executors remain idle for a long time, let's just kill them and go back to, or scale down to the minimum number of executors we configure. And there's one additional aspect here, which is the fact that nodes need to communicate between them in order to get shuffle data from one another. And this dynamic allocation mode needs to have one small service running on each node in order to allow such scaling down. So when an executor goes away because it's idle for a long time, its data needs to be persisted so that the ones that are remaining and need the data that particular node was handling can still get it. But this shuffle service is something that is extremely lightweight and in general does not do much more than just serve some data that is saved somewhere on disk. There's another knob we can turn, and this is something that it's not particular to Mesos this time. This is something that exists in both Yarn and Mesos, and that's the place where the driver process. So remember, the driver is the main application, main Spark application. Where does this guy run? And in client mode, and that's the simplest mode, is on the machine that submits the job, or the machine that runs Spark shell. Now, obviously, if this is a long-running job, and this is your laptop, this is not ideal. Because in the moment you close down your machine, or something happens and it crashes, the whole job is lost. Cluster mode deployment simply picks up a machine in the cluster and deploys the driver on that machine. And in addition, it gets some fault tolerance. If that machine dies, it can be respawned on another node. So let's now try to demo some of these things we talked about, just to make it a little bit more concrete. So I'm not going to install Mesos on any nodes right now. I'm going to assume you have done that, which is not complicated at all. So let's have a look at, pull this on the side, on our Mesos cluster running here in our office in Lausanne. So if I look at Lausanne 1 local 5050, that's the port, the default port for a Mesos cluster. I'll find my cluster. I have 24 CPUs available and 44 gigabytes RAM. And at this point, there are no active tasks and nothing is running. I have only three slaves. It's a small cluster. So if I went to frameworks, I'd have a list of the terminated frameworks because I tried it before. So many people tried things here, you can see. But nothing is active at this moment. And the slaves, the three of them, with their resources, 8 CPUs each, and disk and memory resources. All right, so now if I were to run Spark, I'd have first to tell Spark where the Mesos master is. But remember, or I didn't really mention this, but Mesos is a native application. So we need to tell Spark where to find the native library to run and to connect to the Spark master. So that is done by configuring spark env.shell. This is a shell script in your conf directory. And you need to define this particular environment variable that points to the native library where it is on your system, so Spark can load it and communicate to the master. And the other thing I need to do in Spark defaults, I need to tell Spark where to I need to tell Mesos where to find Spark. So now remember, because Mesos is a very general cluster manager, it has no idea about Spark itself. So there's no way to configure Mesos to know in advance or as a default value where to find Spark. I have to do that as part of my Spark installation. So the variable is Spark executor URI, and you see here I'm passing a tarball. And this is a local path. Now this assumes that all my nodes have this file in the same location, in /opt spark 1.50 bin Hadoop blah blah blah. This is not necessary to be the case. I could use an HDFS file, and in that case, every node should be able to connect to HDFS and download that file from that path. It could also be an S3 URI, and it could download it from S3. So if you're deploying Mesos in the cloud on EC2, you'd probably prefer then to upload Spark somewhere on S3 and download it from there. But for our purposes, this is slightly faster and I'm going to use it in this way. All right, so I'm going to start now Spark shell, and I'm going to say Spark shell, and I'm going to pass the master, which is in my case Lausanne1 local 5050. So let's see what happens. I forgot to put to say that this is a Mesos master, of course. So I need to say master Mesos and then the host name and the port. So while Spark is starting up, let's go back to the Spark, sorry, to the Mesos UI, which is on this place. And I see there are no active tasks, but let's see if there are any frameworks. And I do have one active framework, the Spark shell, which has no tasks. Practically, it's using nothing. I can click on the framework, and I see there are no tasks, of course, as I expected, even though my Spark shell is ready to go. So this must be the fine-grained mode. And indeed it is, because it's the default. So I didn't tell nothing to Spark that I want the coarse-grained mode. All right, so now that I'm in there, let's try to create an RDD, and I'm going to just start with a Scala collection, and I'm going to parallelize it. So I'll say 1 to, let's say, 500,000 elements, and I want 100 partitions. I pressed enter, so let's go back to Mesos, and there are still no active tasks. And this is expected again, because creating an RDD and even transforming it does not actually execute anything on the cluster yet. So even if I said RDD map, and I add 1 to every element, first of all, it's instantaneous, and second of all, nothing shows up in my Mesos cluster. So in order to force such a computation, I need to actually call a method like count on action that basically forces the computation to, well, I need a result. I need to know how many elements are in there. So if I press enter, I'm starting to see something happening. So if I go back here, I see a bunch of tasks already, 20 of them, that are staging. And I can see that they are on different machines, on Lausanne 2 local, on 10.01, 20.10.5, and 20.7, and so on. So staging at this point, this is exactly what I was mentioning before. It means the executors have to be launched. Once they're launched, they finish very, very quickly. And you can see that all of a sudden I have about 100 tasks from 0 to 99. This is 99, 1 per partition, obviously. So I got my result. This is the count of elements, not the sum, that I got back. If I wanted to have a look at what happened, I could go to the sandbox of any of these executors, slaves. These are Mesos slaves, and I would see its so-called sandbox. And in the sandbox, I see it downloaded the Spark binaries. It unzipped them, and then I have the standard error and standard out. I could click on one of those and see what happened. It simply ran a bunch of tasks, and nothing super interesting happened here. All right. So this is more or less the fine-grained mode. If I go back to Mesos, well, I see already in frameworks that my framework is using 3 CPUs and some memory. And this may sound a bit surprising. And this is because even though there are no active tasks, these CPUs are reserved for the executor. So even though the startup time was slow and I had to stage all of these, I had to stage Spark on 3 machines, Spark does not, until it deregisters as a framework, it keeps those executors running. So the second time I run this, it will be much faster. So let's run it again. It will probably, it skips staging, so tasks are much faster to complete, and those CPUs are still there. All right. Let's stop now Spark and try to go to the other deployment option, which is coarse-grained. So I'm going to uncomment this. I'm just saying Spark Mesos coarse true, and I'm going to connect in exactly the same way to the Mesos master. First, I want to go back here and see that there are no frameworks running. So I'm back to square one, and the cluster has all the CPUs back, so nothing is used. So as Spark starts up again, I can go back to my Mesos cluster, and I'm trying to peek. It didn't register yet as a framework, so it will come up in a second or two. Here it is. I have my Spark shell again. It has 3 active tasks, and it uses all the CPUs, 24 of them. So it's a pretty greedy situation. I have 3 tasks. They are all running on all 3 slaves that I have on my Mesos machine. So now let's do the same thing and see if we notice anything. So first I'm creating an RDD, and I'm going to map it and count much faster. So you can see that it pays off to basically choke my cluster with my Spark shell. All the CPUs in one place. All right. There's nothing much more to show at this point because the framework will not release these tasks until I am actually quitting. So I'll quit, and if I go back to frameworks, well, the framework is still there for a while, but it will soon disappear. It went away. Mesos is back to nothing is used anymore. All right. Now the last thing I mentioned was dynamic allocation, and this one requires slightly more configuration. So let's go through them one by one. The first is the Spark Shuffle service, and I need to tell Spark it needs to enable the external shuffle service. And this is required in order for nodes that have been decommissioned, so executors that have shut down, that still have some data they managed, shuffle data, so that can be served to other nodes through something that is not managed by Spark. So not going to show it here, but on every node in my cluster, I have started a process called the Spark, the Mesos shuffle service. And that one is found in your sbin directory, so I can show you here. I had to run start Mesos shuffle service, and this guy goes in the background and keeps running. And I did this on every node. Now, the next thing I have to say, well, dynamic allocation is enabled, and I have to give 2 values for min and max executors. Since I have a small cluster, I say I should have a minimum of 1 and a maximum of 3 executors. And one other thing, which by default is, I believe, 1 minute, is the executor idle timeout. So for how long should an executor be kept running if there's nothing actually running on it, no tasks are there. So I scaled that down to 5 seconds so that it's easier for us to see something happening. So with these changes, I can run again in exactly the same way the Spark shell, and I'm going to connect to the Mesos cluster. So one thing I have not shown you before is the Spark UI. So in addition to the Mesos one, I can connect to my driver, and that runs on localhost, obviously, because I'm using only client mode on port 4040. So if I look here, I see that I have an event timeline showing me some executors. I have to refresh it from time to time. And you can see already that S0 was removed. So this guy was removed because it was idle already for 5 seconds. If you look at the timeline, it started around 42 seconds in, and at around 47 seconds it was turned off. At this point, if I go to Mesos, let's see, I see that I had 3 tasks running. 2 of them were killed because they were unused, and one keeps running. Going back to, is this my? Okay, let's just have one. Here I see that's, yeah, 2 of them were killed. And if I go to executors, I see that I have the driver and S0 who's still there. All right. Going back to the command line, I see some logs that may look a little bit surprising. They're warnings, but this really is expected. So all of these dissociations are nothing more than Spark killing executors that are unused. All right, so let's create, again, an RDD. And this time, let's do something a little bit more complicated. So I'm going to group by modulo 5, and I'm going to collect the data. So I'm using group by here in order to force some shuffle, so that data is not neatly partitioned and no communication between nodes is necessary. So as I do this, there's a stage there that keeps running. So let's go quickly and see what happens. Have a look. A new executor was spawned here because obviously there was some load that needed to be handled. And now I have 3 executors here, or in Mesos terminology, they are tasks. They were running, now they're gone again. So I see again how they were killed. This basically tells me that dynamic allocation is working. I obtain my results, so I obtain an array with all the results. Again, these log messages that I can simply ignore because they are expected. So this concludes our demo. Let's go back and see if there's, a couple more slides. I'll soon be done. What is next on Mesos? So Mesos is still evolving, and there are new features coming up. One of them is oversubscription. So I didn't talk about it, but Mesos offers a way to partition your resources. You can define so-called roles, which are framework roles, and you can reserve resources for a given role. So if I had a role for Spark, I could reserve a number of cores on my cluster that they would only be offered to Spark. Now, this would be a static partitioning, but I would also like to, well, let's leave that for dynamic reservations. Now, the problem with this approach is that when resources are offered, the framework that gets them first can use them, and nobody else can use at the same time. Oversubscription would allow me to offer the same resource to several frameworks, and one of them wins, not necessarily the first one. And this way, there's less probability or less chances for starvation. Of course, you may also have a situation where some of these resources were later revoked, so tasks may be killed. But in general, when an application or a framework runs on Mesos, it should be fault tolerant. It should handle failure. That's part of the game, and Spark does that very well. So it's not an issue. Persistence volumes. These are resources that, after the framework exits, are still around. So if you imagine a database, it would be really bad if one of the nodes are decommissioned and the data that was stored there is gone. You want to be able to persist such things, and persistence volumes are a new feature in Mesos that would allow this type of frameworks. Dynamic reservations are a way to reserve resources for roles, but not at the moment when a Mesos slave is started, but dynamically by connecting to the master and through a series of API calls or through an HTTP endpoint, these reservations can be updated. Optimistic offers are kind of related to oversubscription, and these offers can be revoked. So you may, as a framework, choose or opt in for getting offers that may later be revoked because of higher priority, or these are resources that were reserved for somebody else, but somebody else is not using them. And you may get them, but if that somebody else suddenly needs more resources, you would be preempted and your tasks would be killed and the offers would go to the original intent. So all of these try to make Mesos more efficient in its allocation or more versatile. I didn't really have much time to talk about Spark streaming, but there is one thing I want to mention though, and that is Spark 1.5 resiliency. By adding backpressure. So Spark streaming is working generally by ingesting data at the rate at which it comes. So so-called receivers are deployed on these nodes in the cluster, and let's say they connect to TCP port and starts getting data from there. Now, if data there comes fast, the batch interval at which this data gets processed on a cluster, the batch interval could be too small. It could be not enough to actually treat all the data. So data keeps accumulating, and results come later and later, and at some point you may run out of memory, and somehow this is not a stable configuration, so something needs to be done. The idea here is that backpressure signals have to be propagated between the two main parts of Spark streaming, the execution engine, or Spark core, and the ingestion, the receivers, the ingestion component. So in 1.5, this is something that we at Typesafe have worked on. We added backpressure inside Spark streaming to slow down receivers dynamically based on load. And in the next version of Spark, we'll add the ability to connect to reactive streams. And reactive streams are an industry standard for asynchronous backpressure between streaming components. And this basically equates to propagating backpressure outside of Spark. So instead of just slowing down receivers, which means leaving data in the TCP connection, and eventually the TCP flow control would propagate that, but it's not extremely efficient. Instead of that, just use the reactive streams protocol to communicate backpressure to compliant data sources, of course. So if I were to summarize the key points here, Spark is, as we all know, the next generation compute engine for big data, but Mesos itself is the next generation cluster manager. So it leads to better utilization of cluster resources across an organization. And Spark on Mesos is commercially supported by Typesafe, and we warmly recommend this combination, and we've seen it in production working really well. So at this point, I'm going to pause, and I'm happy to answer questions if there are.
All right. Thank you so much, Iulian. This was a great presentation. Regarding that slide about Spark streaming, it seemed like there was a detail left out, and that is that you and your team are responsible for bringing reactive streams backpressure into Spark streaming. Am I correct?
Yeah, that's correct. So this is work that we've done at Typesafe together. Well, this has been initiated at Typesafe and implemented at Typesafe, but of course we had support from Databricks on getting this to completion. Yes.
Great. There's a question regarding dynamic resource reservations, and it's phrased a little strangely for me, so I'll try to get the message across. Basically, are dynamic resource reservations implemented in Spark so that it pre-acquires resources and doesn't fail in a situation where after executing some tasks it can't find the resources to execute the remaining tasks?
So let me see if I understood. The question is if dynamic reservations are implemented in Spark in such a way that if midway through the job there are no more resources and Spark wouldn't fail. So dynamic reservations are a feature of Mesos. So I assume here the question is more geared towards the Spark part. So I'll try to answer it that way. And if that's not the case, then please restate the question, and I'll try to answer it better. So the short answer is yes. If you're using coarse grain mode, all the resources that can be acquired by Spark will be acquired very early on. And from then on, unless dynamic allocation is also enabled, it will keep those for the duration of the whole job. So now there's some level of control as to what resources or how many CPUs or how much memory it would acquire. But as far as things look today, there's only a maximum that can be expressed. There's no minimum, so Spark would start running even if it can't reach the required number of resources. But this can, of course, change if we see a need for this. So if there's a clear use case, we can definitely add a lower bound as well for acquiring resources. An alternative approach is to reserve such resources, create a Spark role on your Mesos cluster, and reserve these statically for the Spark role. And then Mesos guarantees those resources would be always available, and Spark frameworks are the only ones to get to those.
Okay. Another question gets pretty specific. It says, hi, I have a machine with 256 gigs of memory and 64 cores. What is a reasonable setting for standalone mode? That might be a little tough to answer on the fly here.
Right. I'm not sure exactly what kind of settings we're talking about. I assume whether you should split that into a number of executors instead of creating just one huge, humongous executor. So the main issue with having large heaps, so 256 gigabytes is definitely a huge heap, is GC pauses, and Spark can get confused if it happens to try to communicate to a node during a GC pause and nothing comes back. It would think that machine has died, and it would just kill it and disregard it. So I think, of course, you have to measure these things. But what we've been toying with are sort of heaps of below 64 gigs of RAM. So in your case, you probably go for 4 executors in there.
So 256 gigs of RAM. We've worked with. We would recommend having 4 heaps across that. Speaking of garbage collection, there was another question about Docker and Spark, and a fellow is using Docker and Spark together. Is garbage collection an issue when using these two tools together, and do we offer something that cleans up the garbage? I remember hearing that Docker has a bit of a garbage collection problem in certain scenarios, correct?
I'm not aware of that, so I'd have to. I'll look into it, but at this point, I don't know anything about garbage collection issues when running on Docker. So, and yeah, I did forget to mention that the Mesos executor URI could be a Docker image as well. So I know several people running Spark on Mesos with Docker without any problems. So I'd need to research into this particular issue.
All right. Well, that does it for us today. Iulian, thank you so much for a great presentation. For all of our listeners out there, this has been recorded, and we will be sending you the slides and the video in the next day or so. So look for that in your email. And if you have any questions, you can feel free to email me directly at oliver@typesafe.com. Thank you all very much for joining us today, and stay tuned for the next Typesafe webinar, which will be announced very shortly.
Thank you.
Thank you. Bye-bye.